Okay, so the next question I want to address is question 2. Okay, so we have this circuit. Based on the natural frequency, calculate omega. So omega is given by 2 pi f, correct? Now where's the f? Actually, this 50 hertz is the f. So this is 50 hertz. All right. So that means you just take 2 pi times 50. You get 100 pi, which if you want in numbers will be about 314 radians per second. So that's easy. Now let's move on to question B. So based on the values, determine the impedance of the resistor, the capacitor, and the inductor. So it's also pretty straightforward. So you have to remember all the formulas, right? So go back if you haven't memorized the formulas already. So for the capacitors, apparently for the capacitor 1 and capacitor 2, they're the same capacitance. So I'm just going to write them like this. ZC1 is equal to ZC2 equals to, the formula is 1 over J omega C. Please remember this formula, equals to 1 over J times. Now, what's the omega? The omega is this, right? This 100 pi that we calculated. So 100 pi multiplied by 20 microfarads apparently. So it's 20 like that. This is microfarads. Right? Yeah, microfarads. And then this, if you punch this into your calculator, you should get negative 159.16 thereabouts. Okay. Then okay, for the inductor, the formula is J omega L. Then you should get this. Again, the 100 pi is from the one we calculated times 100 millihenries. So millihenries like that. You should get, punch this in your calculator, you should get this. Okay, so the impedance of a resistor is just its own resistance. So this is 10 ohms. And again, impedance of a resistor is just its own resistance. So 40 ohms, like that. Okay, so determine the total impedance as seen by the voltage source. Okay, so this requires a bit of thinking. When you look at the diagram, in the tank circuit, right, this capacitor, inductor, and capacitor are in parallel, right? The two ends are connected to the same node, which is this node and this node. So they're all parallel, right? This is a whole single node. No device, no device, no device, no device, no device, no device. So they're all parallel. Okay, these three are parallel. So let us call the tank circuit's impedance as ZA. Okay, collectively, all together, they're ZA. So since they're all parallel, we have to use the parallel formula, right? This is question 2, right? Yeah, this is question 2. So with that, we use 1 over ZA is equals to the impedance 1 over ZC1 plus 1 over ZL plus 1 over ZC2. All right, so this is 1 over negative 159.16 J plus 1 over 31.4 J plus 1 over negative 19116 J. Okay, you should get, okay, punch this whole thing into your calculator, you should get negative 0.019265 J 1 over ZA. Then you solve for ZA. So ZA will be 1 over this thing, right? So this will give you 51.9 J. Okay, so you solve for ZA, you should get that. Now, we're not done yet. We have to now look at the resistors. Okay, so what are the arrangement of the resistors? This and this are both in parallel. They're still parallel. Now, let me explain why. It's a bit confusing, right? But actually, see this. Yeah, this whole green highlighted part is a single node. It's a single node. Oh, yeah, that L-shaped part like this is a single node. Okay, why? Because just circle it, ask yourself, is there any device? No device, no device, no device, no device. It's a whole one node. And this too is just one node. So you see, the two ends are connected to the two same nodes, that means they are parallel. So the the total resistance of those parallel resistors, let's just call it R para. So R para is equals to 1 over R1 plus 1 over R2. So this gives you 1 over 10 plus 1 over, what is it, 40 is it? Let me check. Yeah, 40. So you solve for R para, what do you get? R para is 8 ohms, right? So, okay, so that means we can redraw this whole circuit as this. So this is the voltage source. Now I lump this whole thing together as ZA, and this together as R para. Then that means that these two are in series, right? They're in series because they're connected end to end in a serial fashion, okay, end to end. So to find the total impedance, I just add them up, ZA plus R para. So that means the total impedance, as seen by the voltage sources, Z total is equal to ZA plus R para, which is equal to 51.9 J plus the 8 ohms that we got. So this is the answer. Okay. Moving on to question 3. Is the circuit at resonance? If not, what is its resonance frequency? Now, what is the condition for resonance frequency in this question? Okay, in this question, I know there are different conditions that I've mentioned in the past tutorial, but this case is different. So read the question carefully. What did it tell you? Resonance frequency, the frequency at which the magnitudes of the impedance of total L and total C are equal. So this is the condition for resonance in this question. Okay, it's different from the tutorial, so don't mix them up. So follow what the question tells you. Okay, so what this is trying to say, right, is the magnitude, so the magnitude of the impedance of L, so J omega L total, is equals to the magnitude of the total C, impedance of C total. Okay, so this is the condition they are trying to tell you. So are they at resonance? Let's check if this condition is true. Okay, so let us go ahead and do that. Now, what is L total? In this case, there's only one L, right? So L total is just this single L. But what about C total? Now in C, there are two capacitors, right? C1 and C2. What is their arrangement? Their arrangement is actually parallel to each other, right? Notice that they are parallel. C1 and C2 are parallel. And what is the total capacitance in parallel? The formula is just add them up. So C1 and C2 are parallel. You just add them up. C1 plus C2. That's it. Okay, so C total is given by C1 plus C2. Okay, this is because they are parallel. If they are in series, you have to use the 1 over C1 plus 1 over C2 equals to 1 over C total formula. Okay, but that's a different story. Okay, that's a different story. So okay, let's check if this condition is true. So check. Okay, so let us check ZL total, right? They say the magnitude of the impedance of the capacitors, sorry, the inductors is the magnitude of this. This is what we got earlier. Okay, this is what we got earlier. So since it's just imaginary, the magnitude of this is you just take this coefficient. So it is just 31.4. That's the magnitude. Then ZC total, right, is given by. Now, notice that C1 and C2 are exactly the same, right? So I just take 2 times one of them, which is negative 159.16 J. Okay, you find the magnitude, you should get this. Okay, so this 318.31 is just take this times this. Okay, you don't need the negative sign anymore. You don't need the negative sign. Then you should get 318.31. And then just drop away this J. So this is the magnitude. Now, ask yourself, are they the same? No, they're different. So what does that mean? They're not at resonance. So not at resonance. Since this magnitude is not equal to the capacitance magnitude. Okay, so we show that they are not the same. Okay. Now what did they ask? If not, what is its resonance frequency? So how to deal with this question? So remember, we had to make use of the condition they tell us. The condition they tell us is this condition, sorry. So for resonance, we need this condition to hold true. Okay, so that means that this is equal to what? So what is the capacity? So what is the impedance of capacitors? It is 1 over j omega c, right? But then in this case, I'll call it c total. Then what is the impedance for inductors? It is j omega L, right? So what do I have to do? I have to solve this equation for omega. That omega will give me my resonance frequency. So what should I do in this case? In this case, I had to take the magnitude of this. So magnitude of a complex of a purely imaginary number. You see, this is purely imaginary. There's no real part. There's an imaginary part, but there's no real part. So I just take this omega L. I just drop away this J. So this is omega L equals to. Now, how do I deal with this? So to deal with this, the intermediate step is this. So remember, when you see 1 over J, you can change it to negative J, right? So I'll change it to negative J, and then everything else you copy down. So 1 over omega C total. Okay, don't forget the absolute. So when you take the magnitude of this, you can drop away this negative, and then you only take the part in front of the J. So you just take this part. So 1 over omega C total. Okay, so now we have to make omega the subject, right? So omega, this omega, I move it here, so it gets omega squared, and this L, I move it down here, so it becomes 1 over LC total. Then this square, I bring it to the other side, becomes square root. So square root of 1 over LC total. Okay, now I have to substitute in the values. So this becomes square root of 1 over 100 millihenries times 40 this. Okay, how do I get this 40, right? Remember, C total is given by C1 plus C2, and then they are both 20 plus 20 microfarads, right? Oops, sorry. They are both 20 microfarads. So that's how I got this 40 microfarad. Okay, so this is how I get this. Then if you put this in your calculator, your omega should be 500 radians per second. So this is your resonance frequencies. I'll just put resonance here, resonance. Okay. Now, last question. IV. Yeah. Did I miss anything? Oh, sorry. I should label this here as question 3. So for part 4, what is the total impedance at resonance frequency? Okay, so this is a bit of a crazy question that I don't think I got correct in the actual exam, but I've checked this with Professor Lee Hong. So what we have to do is we have to find the total impedance again. Remember just now we found that whole process of finding the impedance, but now instead of saying omega equals to 100 pi, remember originally we say omega is 100 pi. Where did I get that 100 pi from? Here, remember? See, this is the 100 pi. Remember we said omega was 100 pi. This time we will substitute omega with 500 radians per second. Because they said this time is at resonance. At resonance, what do we say? Resonance, the omega is 500. So this time we will substitute omega equal to 500. So what do? I find the total impedance again, but this time, every time I see omega, I sub in 500. So let us do that. Okay. So ZC1 equal to ZC2, because the capacitance is the same. 1 over J omega C, right? J omega C. So remember, previously this was 100 pi. This time I'll just put it as 500. Put this in your calculator, get 100j. Then ZL is equal to j omega L, j omega L. You get 50j. Okay, remember, this used to be 100 pi. This time I put 500. Okay, then you find the impedance of the parallel, the capacitor C1, L, and C2, right? So this is in parallel. So 1 over ZA equals to 1 over Z C1 plus 1 over ZL plus 1 over Z C2. You substitute in the values, you should get 1 over negative 100j plus 1 over 50j. Now, here comes the funny bit. Punch this into your calculator, right? You'll get 0. Okay, you get 0. Now you want to solve for ZA. So what does that mean? ZA is equal to 1 over 0. But then, what is 1 over 0? Undefined. Okay, so this is the answer. Apparently, it is the answer. I never got undefined. I think I got some finite value, but then this is the correct answer. Don't freak out. This is the answer. I think this is a borderline somewhere out of syllabus kind of thing. Okay, don't take my word for it. But it's really meant to throw you off. Okay, apparently for RLC, this is a RLC circuit. Apparently for RLC circuit, when it's at resonance, the impedance is indeed undefined. I thought this was crazy. I checked this with Professor Colin. He said, yes, it is the answer. So yeah, take it as it is. I didn't get this answer correct when I was doing this paper. So it is what it is. Yeah, I guess I'll move on to the next question. Okay, so what's the next question? So the next question states to draw this on the Gauss plane, aka the Argand diagram. So C. So of course we need our imaginary axis, real axis. Oh, that's very ugly. Real axis, imaginary axis for each of the device. Okay. So earlier, what do we get? Let me just pull up my values. Okay, so ZC1 is negative 159.16J. So this is what we calculated earlier. So this is on the imaginary axis, right? Because of this J, and it's on the negative side. So it's down here. Down here. So this is negative 159.16. So this is ZC1. It's also ZC2 actually, because they're the same thing. And then ZL. So ZL is 31.4J. Again, it's on the imaginary axis, but this time it's positive side. So this 31.4, this is ZL. Okay. And then the resistors are 10. So this is 10. This is ZR1, which is 10 ohms. And then another one would be what? Let me choose a different color. Let me just make this thicker. So it would be 40 ohms. This is ZR2. And is that all? The resistor, capacitor, inductor, and the total impedance obtained into will be 2. So the total impedance that we obtained earlier just now was what? It says 8 plus 51.9J. Okay, so 8 is somewhere here, and then 51.9 is somewhere up here. So we'll just mark it like that. Like that. Like that. Let me just put a different color. Okay, so this is Z total, which is about 8 plus 51.9J. Okay. Obviously you should make your sketch neater than mine. Okay, use a ruler and try to roughly get the scales correct. Don't have to be exact, but you get the idea. Okay, so that's it. Okay, if the voltage source can be represented by a unitary phasor, determine the phasor of current I. Okay, passing through the voltage source and the voltage across the resistor R2. So what we want is the I through the voltage source. So in this case, we need to use the Ohm's law in AC setting. So V is equal to I Z. In this case, Z total. V is what they told us. So let us go back. It says there that Vs is given by this, right? Vs is a sine function. And then they tell us it's a unitary phasor, sine, 100 pi, like that. They don't tell us any phase. So let us convert this to a phasor, which is 1. This is, we change this to cosine first. 100 pi minus 90 degrees. Okay. Then this as a phasor would be, you take this and this. That would be 1 at an angle of 90 degrees, negative 90 degrees, like that. So this is the phasor of Vs. So let us go back down here. So this is 1 at an angle of negative 90 degrees, which is equal to, this is what we want to find. The Z total we got is 8 plus 51.9J. Okay, you make I the subject, you take this, negative 90, divided by this. And let me see what you get. I didn't find the answer for this, but hopefully it should be right. Okay, give me a minute. Okay, so 8 plus this answer, and then we have the phasor, which is 1 at an angle of negative 90. So let me just change this to polar form. You should get this at an angle of negative 171 degree. Did they ask for phasor or time domain? They asked for a phasor, so I can just leave it as that, like this. Yeah, so punch this into your calculator and then convert it to polar form, you should get this. As well as the phasor across the voltage, phasor of the voltage across R2. Now, let us go back to the diagram. Now, we want the voltage across, it is just like saying the voltage across R2, right? The voltage across R2 means the delta V across these two nodes, right? Which is apparently the same for R1 also, right? R1 also shares the same voltage phasor with R2 because they're parallel. Okay, so that means if we want to find the delta V of this, we just need to find the delta V of this R parallel. Okay, we need to find this. It will give us the phasor across R2 also. It's the same thing. Okay, so find this. So how do we do this? We use the potential divider. Okay, so potential dividers will state that to get this VR2, which is the same as V parallel, okay, this does the same thing because they're parallel. It will be R para over ZA plus R para times the input voltage, which is Vs. Okay, let's use this formula. This, copy it over, and I paste it down here. So R para we got earlier is 8. So 8 plus the total impedance that we got is 51.9J plus 8 times the V S, which is this. One at an angle of negative 90. Okay, let me just punch this in my calculator, see what I get. Okay. One at an angle of negative 90. I'm going to change this to polar form. I got 0.152 at an angle of negative 171.24. Okay, so this is my phasor. I can't tell if my answers are exactly correct, but I can tell that my methods are correct. Okay, so yeah, that's question D.